Welcome back, guys. I'm gonna mute. Does it work out for you, Brian? Does it work for you?
Is the first slide the behavior of gases?
Yes, it's a simulation.
And is there 77 slides?
Yes, is that a lot?
Yeah, okay, I'm in.
It's 77.
The link's not here.
What's not here?
The link.
I don't know if that's Harry as a baby, but
Can I put this link in the chat for you? I think it'll be faster than if I log in. If you need the link, I'll put it in the chat. Okay. Here it goes. That work?
Wait, can you just oh wait, I'll just use the code.
Also, click on the link in the chat as well.
Okay.
Are you on? Are you all on?
Wait.
There's a code in the chat that you find that convenient. That takes you right.
I'm just signing in.
Okay. Hi, Isabella. You can get in the slideshow through the chat. I put in the link through the chat. How you doing, Brian? Give me a thumb up if you're okay.
Yeah, I got it.
Okay. How you doing, Brian?
I'm good.
Good, okay.
Wait, is it like the slides of the?
Wait, hold on.
Oops. Yeah, I'm in.
Okay, great. So the slide is 77 slides, starting with the simulation. So
Yeah.
in our last class, we're going to continue our conversation. And you notice this section is more towards the physical, still continuation of physical science, but more of the chemical aspect of physical science. We're going to be diving into something like the structure, the energy level in an atomic structure, bonding, chemical reaction, things that I feel like it's interesting. If I feel like it's interesting and worth, we'll do that as well. Okay. Welcome back, all. Ask me questions anytime, any suggestions, but do believe that we have a handful of students. So in order for everyone to hear me, please raise your hand or have your thumb up to participate and wait for your turn. So Ben, you had your hand up. You have a question?
well, it's irrelevant, so I'm not gonna say it.
It's okay. You can.
I just feel like I need to point out the name Young Yards Drive Lovely Grapes. Like, what is this? What is this?
I think, sometimes it's hard to put these mnemonics together and they just come with the name. You can think about like, this is a person, right? Like a young lady driving something. I don't know, it doesn't make sense, but
Yellow jacks.
It's just fun. Hi, Isabella. How you doing? You getting in the slideshow? Are we good? All right, let's begin. So in our last class, we had conversations about matter, the different states of matter. We talked about the physical, chemical properties. And today we're going to dive into the behaviors of some of these matters and take a look at how they behave. So jumping in, we're going to start with a simulation. If you get into the simulation, click on that end, you will see like 3 to 4 different choices. We're going to go into something called ideal. So when we talk about behavior of gases, we're really thinking about a hypothetical, perfect utopia condition, right? Of course, this does not represent what is really happening. An ideal situation never happened in the real life. But we have to find a specific condition that everything, all the factors agree upon each other. So let's go into the ideal gas condition. Give me a thumb up if you're in the simulation. We have some sort of access to this. So I want to give you like a few 30 seconds. Right? Take a look. What are some things that you can conclude about the behavior of gases, right? So come up with like a small list of things that behave, right? So it can start you off with, there are like something called...
Oh, you can heat. How do you get in?
How do you get in?
Yeah.
Okay, so if you're on my slideshow, there should be like a link you can click on. Does that
Yeah,
work?
but it doesn't
There's
work.
a lid. I can make it explode.
Okay, so ladies,
Same. You have to like heat it up.
if you
And also
can't
add
get
another
in-
Oh, I'm in.
if you can't get in, again, I'm gonna paste the link in the chat. Okay, guys, just bear with me. If it's in the chat, you can just click on it and save it. For your,
The old one, there was way less gas.
Okay.
Like it went out way slower. Oh, there's 2 types.
okay, so there are 2 different type of gases. Now watch this, guys. You know, I can release some gases in there. Not too much.
Why are yours red?
I want to
You
release.
can change them. You can change them from blue to
I put
red
too
at
much,
the bottom. See?
I put too much, guys. I'm gonna let go of some. It
I'm
doesn't.
gonna heat my 1 particle up.
Okay, so I can go increase the heat. I can bring in more. I can cool it down with some ice. This is really cool, right?
I'm heating my 1 particle up by a knot.
Okay, so watch what's
Oh my
happening.
god, it's at 5,000 Kelvin. 7, 8, 9, 10,000.
Okay, so and what else can we do? We can
Pull
change.
down handles.
So there are things that we can keep constant, right? So think about what are some factors that can affect the behavior of these gases. All right. And so what are some conclusions you can make just based on our initial observation of gas particles? What type of behavior that gases follow? If you want to release and restart, try it out with different gases. Pump a little bit. What are some things that you can conclude about gases and how they behave? Can we get someone, Michelle? What is one thing that you can say about gases and how they behave?
One thing that I can say about gases is that it has no solid form.
So they're not solid. Is that what you're saying?
Yeah.
Okay, good. So gases are different from solid states. Good. What can you conclude from this? Brian, what is one thing that you observe from this simulation?
They'll explode if you have too much pressure on it.
Can you say that one more time, just slowly?
They'll explode
Okay.
if there's too much pressure on it.
So it can cause the change in pressure. Very good. Thank you. Isabella, what can you say? Your mic doesn't work. Feel free to type in the chat. Does your mic work? We'll come back.
Oh, it's like a slow-mo. I get to see like slow-mo explosions.
So let's get to Ben, then Harry. Okay, Ben.
So I pumped out all of the little the what's it called part I forgot what it's called.
These are called gas particles.
Yeah. And then I pumped out all of them for both blue and red, and then it heated it up so much that the lid just came off.
No, guess what? I heated up 1 particle to like 70,000 Kelvin, and then it said that was the limit. So then I couldn't heat it up anymore. But it
You
didn't
heated
explode.
something up to 70,000 Kelvin?
Yeah, it goes up exponentially.
All right. So Ben, finish up your statement. So why do you think the cap popped off? What was
Because
created?
they were moving too fast.
And what is formed as a result of those collisions?
Pressure.
Pressure.
There's definitely pressure that that requires more room, right? Is there a limit how much particles you can put in the box?
Yeah, well, no, you could just make it a black hole.
No, you can get all of them out.
But the lid will explode.
Yeah,
It'll
eventually.
explode, right? Why do you think it explodes?
Well, the lid won't explode. It'll just fly off because
There's just too much pressure.
It's too much, right? So eventually, if
it's just too much.
if I put too much air in my ball, then once it runs out,
Bye ball.
it's gonna just get destroyed. All right. Jason, do you have anything to add?
No.
Harry, do you have anything?
I want to say the same thing. Yeah.
How about Kevin? Kevin, are you there?
Yeah, I was just switching tabs from the presentation.
Are you able to get in?
Yeah, I was just getting into a presentation.
Okay.
Wait, which on the ones on the simulation do I click?
Ideal.
Okay.
So I'm gonna come back to all of this, and you're gonna have more time to play with this at the end. But let's go back to our conversation about behavior gases, right? So you saw there's a lot of interesting things about behavior gases, and scientists are super fascinated with how they can behave because they have a lot of real life applications. So today we're going to talk about some of these behaviors, right? So which of these representations represent a
I
gas?
got it to 0.
Which of these represent a gas?
The one on the left.
Right. So this looked like something right here, right? So when you have gases, they are really just flying all over the place at a given time. What's in between gas particles?
Nothing.
Lots of empty space, right? So there's a lot of room, which is as a simulation here. So moving on to gas particles, right? So this is a review from last time. What is defined as a gas? Particles, they don't have any shape or volume. They just take up whatever is surrounding, and they can be compressed. What does that mean, they can be compressed?
You can make them take up a smaller space.
Okay, so let's take a look at the simulation. Has anybody seen this?
And then they'll have more pressure and stuff.
And then the lid
Because they have nowhere to go.
And then the lid will pop.
Okay, so if you
Probably.
if you can raise your hand if you want to speak something, I'll call on you, okay? So then you don't end up overlapping one another. So what do I mean by compressing? Let's have, I was gonna call on Veronica. Ben, what do I do to compress? I have a system. What is the name of the system?
What do you mean by naming this of a system?
In front of my screen. Look at my screen. I have another simulation up.
Uh-huh.
What do you see? What type of system is this?
I see a syringe.
A syringe. Next question. Is the syringe an open or a closed system?
Closed.
How do you know?
Because it looks closed and the gas molecules aren't escaping.
Good. So the gases are contained inside and we have a seal at the end, right?
Yeah,
So
also because I can see it.
why is the plunger of the syringe moving up and down at this point? Someone else, Ben, thank you. Michelle, why do you think this plunger right here, right? This plunger, when I mean this plunger, why is it moving up and down a little? Okay, give it a try. What do you think? Why do you think it's moving up and down? Is something moving it? Or is it, what is it? Do you see anything that's happening? Or do you want to pass it on to someone else? Michelle, do you want to pass it on to Jason?
Yeah.
Okay, Jason, go ahead. You want to take it over? Why is the plunger moving up and down?
I think the gas molecules are pushing it around.
Yes. What do we call that? These little gas particles, when they are hitting the walls of the system, what is created? What do you call that? Collision along the walls of the system. If I hit the ball, what am I creating? I'm creating a lot of pressure. So there's a lot of pressure,
Yeah.
force or pressure, right? Going back to the physical part of it. So if I compress, what do I do in order to compress the gases?
You push the plunger down.
Down, right? Now, if you have a system, you can try this. Is really cool. I do this inside in-person classes. You can actually create this system. You can push it down really easily. Now, why does the plunger coming back up as I'm releasing my hand?
Because the gases, they're moving around and they want to push the plunger up.
So again, we're talking about forces that's generated when the gas particles are hitting one another, right? Hitting the walls. All right, great. So we have a pretty clear visualization of what is happening, right? So how do gases behave? This is the section where the simulation comes in. So when we talk about gases, we use what's called the kinetic molecular theory. what is kinetic molecular theory? It stands for moving molecules. It's a well-supported, documented idea that moving particles are moving in a different way. So let's take a look. Let me know if the
Kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. These particles are sparse and move around freely. Gases are usually invisible to the eye and they can be expanded and compressed in different pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory.
All right, so let's go back. Based on your observation, what is kinetic molecular theory? If I ask the question a little differently, why do particles, gas particles, move around? What do they possess? Jason?
Kinetic energy.
The kinetic energy, the energy of motion, right? You can't get around with it. Thank you very much. So let's take a look at some of the basic principle of kinetic energy. Okay, so someone was saying, like, what do I call these little dots, right? These are particles, and what they are molecules of different gas particles. When you go back to the simulation, you see these are, does it tell us what it is? What is the purple one? Does it give us a particle name? It doesn't give us a particle name, but these are just representing different gas particles, right? There are no attractive or repulsive forces. So when you're looking at these gas particles, are they attracted to each other? Are they sticking to each other?
No.
Are they repelling from each other?
No.
Okay, so in an ideal, remember we're in that ideal situation, there's no forces. And what's in between the gas particles?
Empty space.
Lots of space, right? In a given time, there's a lot of space. Right, moving from there. And this is just like information, but it's better that we understand it. So how are they moving? Are they moving in a specific style or they're moving randomly? Do they move in straight lines or do they curve around?
Well, it looks like they move in straight lines.
Okay, good. So from kinetic theory, kinetic energy theory, molecular theory, they move in straight lines until, right?
They bounce.
They bounce. So watch what happens. A slow motion. Right, the minute that they collide, well, what happened? They switched.
Some energy, so one used to be fast, the red one was fast, and the blue one was slow, and then they collided, and then they both turned purple, which was, they're both moved at the same speed.
So they go straight lines, so they go random, they go anywhere they can be possible. They want to spread out as much as possible. Once they hit, there's a transfer of kinetic energy. There's a passing of kinetic energy, and they go opposite directions once that collision moves around, right? But in an ideal situation, there's no change in the kinetic energy. And this is only when there's an energy transfer without the loss, which means, right, they'll get more or less, but the overall kinetic energy is the same. So gas tend to diffuse. Does anyone know this word diffuse? What does that mean? Diffusion. Does gas particles move around quickly? Yes, right? So they diffuse, meaning they go into different areas. If there's an empty space, just like the subway cart, people try to sit as far apart as possible, especially now. Did you guys saw that video today? This guy is on the train. Somebody tried to sit next to him. So he split up his legs to block people from sitting next to him. That's kind of like how the gas particles behave. They want to be as far apart as possible. And they go from a high concentration to a low concentration, right? So if somebody spray like a perfume at the corner of the room, pretty soon you're going to smell it on the other side of the room, because that concentrated particles will be moving towards a lower concentrated area. Pressure, right? We talked a lot about these gas particles. They bombard. When you look at the system, right, they are constantly creating these forces that's causing pressure. And when you're trying to pump so much of that gas in there, you can pump it so much, Ben, that the cap pops open, right? The walls is not able to support that amount of pressure. And at points you can cause explosion, right? Like the balloons can pop. Okay, what else? Does anyone know what this is? Bonus credit if you can name this. Actually, I'll give you a hint. It's right on there. Jason, what is it called?
Mercury barometer.
It's a barometer. Yes, it's made of mercury. Okay, so let's talk about barometer. What does barometer measure?
Pressure.
Yeah, go ahead.
It measures the pressure.
Yes, barometer is a weather instrument that measures air pressure, not water pressure, right? What is mercury? What do you know about mercury?
It's a very dense element.
And can we eat it and play with it?
No, you shouldn't, unless you want to die.
Okay, so
That escalated quickly.
this is more of a recent discovery that mercury is toxic, right? It can cause brain damage. But when I was growing up, around my house, it was all filled with mercury thermometers. Now, why do we use mercury? Because it creates, we'll talk later about, like, not in the next class, how.
So it's dense, which means that, never mind.
Mercury is more accurate when you are making measurements. Okay, because of its properties it possesses, but it causes brain damage. So they're still using it in labs, which are with care. Now in classroom, we're no longer allowed to use mercury because they really do mercury. Instruments can break very easily. They're usually inside of class. When I was a kid, I was telling you that it's made of mercury. We have thermometers that are made of mercury, and I broke one, and the mercury came out, and it is like the coolest thing possible. Do you guys like slime? Raise your hand if you like slime.
Isn't it deadly?
Yeah, this is better than the slime, guys. This is so cool. It's like that Nickelodeon show. I can't remember the name of the show, but this person changes into like a slime thing. But definitely not good for my health, right? It can cause damage, a long-term damage. You can't see it immediately, and also depending on how much exposure. Anyway, that's aside the point. I get really excited when things pop up like that. So avoid touching mercury. Barometer is something that will measure pressure. So can anyone describe how barometer works in this simple setup? This is a very classic way of setting up. And what you really have is a dish filled in with mercury. Then you have a test tube, a glass tube, and you've flipped over, right? So how does it work? How does it measure air pressure?
So the air presses down on the mercury, which makes it rise in the tube.
Yeah.
But the more it rises, the more the mercury also gets pushed by the mercury that's already on top of it. And then there's a balance. So the higher the air pressure, the higher the mercury goes.
Perfect. Yep. So it's a simple thing you can actually set up in the lab, right? And you can see, like, you're exposed to mercury when you're using this. What people didn't know, it was harmful until recently. So when air particle, right? When I talk about air particle, think about these, right? A lot of them, they're moving around. They're causing forces, which is a result of pressure, which results in pressure. So I can close that one. So once that pressure is hitting onto the mercury, it causes a rise, right? The increase in the mercury level tells us how much pressure there is, right? So So the more pressure, the more increase. So how do we measure, what is the air pressure? Well, air pressure is the air particles that's exerting the force against our body, right? Now, in a closed system like this, right, there's air pressure in here. I can measure the pressure. So when we measure air pressure, when we talk about air pressure, we can have like different units, like mercury, and that's where the old barometer, their barometers that go in by atmosphere, and then torrs, and pascals. If you look on the bottom, there's pascals down there. There are different measurements units, but when we are referring to air pressure, we're usually referring to like a standard temperature and pressure condition, because under the standard condition, gases behave in an ideal way, right? It's called standard temperature condition. What does that mean? It means that it's at 0 degrees and it's at 1 atmosphere pressure. So as we know, right, like if you change the temperature, what happens to the gas particles? They will change in their behavior or no? They will. If you decrease the temperature, will the gas particle behave differently? Yes, they will, right? They will slow down. So by keeping, when we're studying the air particles, by keeping at a standard temperature and pressure condition, we are able to monitor its overall behavior. So what are some factors that affect pressure of an air particle? What are some things that can affect the amount of pressure that we have built into the system? Does the temperature affect it?
Yeah.
Okay. Does the number of particle affect it? Does the volume affect it? If I can decrease or increase the volume, does that affect it? So those are different factors that can essentially affect how much pressure that's building into a system, right? I can decrease the pressure volume. I can increase. I can change the temperature. So what does that tell us, right? So if you increased the amount of gases, why don't I ask you this, guys? Just let's take a look at this if you can conclude, right? If I increase the number of gas particles, how does it change? Why is it not doing anything? Why is it so slow, guys? Try it again. If I'm increasing the number of gases, how does it change the air pressure there?
More particles are bouncing on the edges, which means more bounces occur, which increases the pressure.
More pressure. All right, now let's talk about volume. If I decrease the volume, how does that change the pressure? So I went from here, someone else, okay? Michelle, if I decrease, look at, I'm dragging this box, I'm making the box smaller. How do you think the pressure change as I'm decreasing the volume of the system and keeping everything else the same?
I think that the pressure will increase because there's less space for the gas. Yeah.
There's definitely a lot more pressure because you got more, right? So the same idea here, this is a different system. If I'm pushing them together, I'm decreasing the volume. Now they're bouncing it a lot more. It's bouncing more. When I let go of my hand, that pressure is pushing that plunger back up. And we can actually show the pressure gauge to see the changes in pressure. All right, last one. What else is affecting the pressure? We mentioned volume. We mentioned the number of particles. What else is affecting it? Brian, what else is affecting it? What else is affecting the pressure? It's volume, number of particles. What else? What is one last factor?
Temperature.
So if I'm increasing the temperature, the volume, how does that change your air pressure?
If you make it hotter, it increases. If you make it colder, it decreases.
Good. So why does it increase? Why does the pressure increase when I heat it up?
Because they have more energy to move around.
There's a lot more kinetic energy, more bouncing, more collision. When you do the writing, make sure you, so there are some examples of an amount of air, right? So when you are in different seasons, you're gonna pump your tires a little differently depending on how they're behaving. Car tires temperature deflation in the winter, right? When you're decreasing, the tire tend to get less deflated. It gets deflated, so you want to pump more air in the wintertime and less air during the summer. You guys go bike riding in the summertime?
Yeah.
Yeah, a lot.
Secure your tires. Yeah, that's probably one of the outdoor activities I do, and I have to make sure that in the summertime when it's really hot, I don't pump a lot of air, right? Because the pressure can increase and I can pop my tire. Volume, pressing down on the balloon and it pops, right? Simple principle, guys, but this leads to some like really fancy relationships that scientists have studied for centuries, right? So pressure and volume have inverse relationship. So there are three factors: pressure, volume, temperature. When one of them is constant, there's some relationship with the other one, right? So pressure and volume has an inverse relationship. What does it mean when we say inverse?
Opposite.
Opposite, right? So pressure goes up, volume goes down. Pressure goes up, volume goes down. Volume gets smaller. If I increase the volume, pressure goes down. Inverse relationship. So that is what this is called Boyle's law. Of course, you don't need to know this, memorize this, but this is just like a relationship, like a relationship that will come in handy when you go on to high school studies. They're going to be like very helpful, right? So this is a representation of an inverse relationship. If I know a system with this type of pressure, I can calculate the pressure and volume in another system by making that relationship. All right, so this is a representation. This is just a simulation showing you like an inverse relationship. But how would you draw an inverse relationship graph? If I were to sketch this, what does it look like? Isabella? Jason, what does it look like if I were to draw this graph? Pressure and volume has an inverse relationship. What does it look like if I had to draw it on the graph?
So the smaller the volume, the bigger the pressure. So like,
I'm gonna put my first dot over here.
so then
Like that.
and it would go down, yeah.
So a good thing to have in your mind, like a exponential, like a decreasing, the backwards negative slope. You learn about algebra, you take it algebra. It has a negative slope, right? Great. Can we move on? Clear this? All right. What about volume and temperature? What type of relationship do they have? Direct relationship or inverse relationship?
Direct.
Direct, right? So they increase the temperature, volume will go up. If pressure is hold constant, right? So if you want to change, if I want to keep the pressure the same by closing it, or by want to keep it the same, return the cap. And if I increase the pressure, the volume will have to increase to keep the pressure the same. That's where that came from. So let's draw the graph. Tell me what to. This is called the Charles law. These are different people, right? When you discover something, who you're going to name it after. You're going to take your own name and write it on that piece of paper so people can remember you, right? So these are the guys that study these relationships. It's easy to look at it now, but when you are, think about these things are invisible, right? They're so tiny, we cannot see. So to be able to conclude these relationships takes a lot of experimental design. So how do I make this graph? Michelle, tell me how I make this a direct relationship. What does the graph look like? So what do I do? If the temperature is low, is the volume low? Yes, right? So they're the same position. So what do I do next? Do I put it here? If the temperature going up, volume goes If the temperature goes up, the volume goes.
Volume goes up as well.
Right, so you'll see like this positive relation. I'm going to show you, like, this should be a simulation, but okay. So that works out, right? See, once we examine that simulation, we're able to conclude this relationship with such ease, right? Pressure and temperature, what's the relationship? There's a positive relationship. If you increase the temperature, the pressure will increase, like Brian said. There's going to be more kinetic energy when you are increasing the temperature. Therefore, there's more pressure. Does anyone know who came up with this relationship? Do you know the name? You guys heard about that name? So they're like different people that made up these relationships. There's the direct relationship going there, right? So this is the combined gas law, which will come in handy, right? That's how you remember P and T has a direct relationship. Volume and temperature have a direct relationship. P and V, pressure and volume, has a indirect relationship. All right, so we mentioned that ideal gas law. These laws, kinetic molecular theory, only behaves in an ideal condition. When does the ideal situation, what is the condition that we have to create to meet the ideal situation? The gases are most ideal when we have high temperature and low pressure. So that way, the gases are moving really fast. They're not sticking to each other. So because that is hard to accomplish, because when the temperature decreases, gas particles start to stick each other. Why is that the case? What happened when you lower the temperatures? What happened to the gas particles when you lower the temperatures? Why do they stick to each other when you lower them, when you lower the temperature?
They don't have that much energy to move around.
Perfect. Very good. When you take away that kinetic energy, they're going to start melting. They're going to start condensing into liquid, right? So then they're going to start behave like liquid and eventually into solid. Beautiful. When you have a high pressure, gas occupies a specific volume. So just keep in mind, there's no perfect condition, and gases are, with steady gases, the ideal situation. So in a sealed container, there's something called a vapor pressure, right? Just like the pressure, there's a special type of pressure called vapor pressure. Vapor pressure is important when we're talking about boiling point. Now, this is a little difficult concept to grasp, but what it really is evaporation happens when particles of the liquid causing pressure to build up above the liquid.
Your voice is freezing for me.
What did you say?
Your voice and video is freezing for me.
Is that happening with everyone else, Jason? Is that happening to you?
What?
Is your screen freezing?
Well, everything just
No.
froze for me.
Well, then I think Kevin has a bad internet connection.
But you're frozen on my screen.
You have the slideshow open that you can follow my slideshow on the separate.
It says my internet connection is unstable.
Maybe you open a window or something that works for me. So I'm closing some of my simulations so that will reduce some of the lag. All right, so this is an image, right? When you think about vapor pressure, some of the liquids are evaporating into a gas particle, and the gas particles are creating the vapor pressure. How do you increase the rate of evaporation? How do you make the water evaporate faster? I have a wet floor right now. Like my ceiling is leaking. How do I make the water go faster? Jason.
You heat it up?
I want to heat it up. Okay, good. Increasing the temperature. What else? Ryan, how do I make the water evaporate faster? Oh, and the answer is on the board.
Increasing the surface area.
What does that mean? What does that mean, increasing the surface area? I'll take the water from a small bucket, put it in a bigger bucket, right? So that more water is exposing to the atmosphere. Would that explain the surface area? Does that work?
Okay.
You move from one big small volume area to a bigger volume. All right, great. And when you want things to dry faster, what else do you do? Like I wash my hair. How do I dry my hair? How do people dry their hair? What's that machine they use?
They use a blow dryer.
They use a blow dryer. Do you guys use blow dryers? Do you want?
I'm fine.
Yeah, I use it because not only it increases temperature, it creates an air current to allow the air particles to move around faster. All right, so when these gas particles are emitting from the liquid particle when they're evaporating, there's gonna be like a balance between the amount of gas particles within the jar. This is called a flash.
Froze again.
Froze again.
Yeah. Okay, it's a little better.
So, does anyone know what this is called? I just mentioned the name of this container. What is this container called? These are nice.
It's a beaker.
It's a flask. It's an Erlenmeyer flask. It has that special shape. A beaker is more like a graduate. It has a cylindrical shape. All right. So when there's a equilibrium, what does the word equilibrium mean?
Equal.
Balanced.
It means equal. When there's the same amount of, when evaporation, condensation equals to each other, it has reached the equilibrium. And that equilibrium is what we call the boiling point, right? So when that equilibrium reaches, it's gonna have that boiling point. So when you are boiling, heat energy overcomes attractive forces, right? So you had to break those molecules apart because they're attached to each other and allow them to move freely into the gaseous phase. So you had to break something called the intermolecular, the forces in between each molecules. I don't know, like a simple example in evaporation, I'm gonna have to separate the cap and the body of the pen, let them go freely. So if you have a very strong force between molecules, you're gonna need more energy to break down that connection, right? So I have a question for you. Which one has a higher boiling point? Water or alcohol? Ethanol, alcohol. Which one evaporates faster? Alcohol or water?
Alcohol, I think.
Yes, how do you know?
Because I heard somewhere that water, it requires like 4 joules just to heat up a gram.
Yep. We're going to talk about that.
That's the specific heat.
Yep. So alcohol, the minute that I use a lot of alcohol nowadays to clean, the minute it reaches the surface, it evaporates within a second. It has a very low boiling point. Why is that based on here? Why does alcohol has a low boiling point? Because the alcohol particles have a smaller attraction in between the particles, right? So they separate very easily. Just take a few joule of energy to separate those molecule forces. Water, on the other hand, and transitioning into a conversation of how liquid behave, there's very strong forces among water molecules, which allows this really high boiling point. It requires a very high temperature in order for it to rise into the gaseous phase. All right, so here are some applications. What happened to this gas when you place them in a high pressure? This is something that I'm really scared to use because I'm afraid that it will pop, but it is measured, it's managed, right? So there's a gauge here that you can slowly release that pressure. Now, if you release it too fast, too much gas will come out, right? Because in a very small container, there's a lot of gas particles. Now, what happened if you lower the temperature of gas particles? This is liquid nitrogen. What happened? What happened if you lower the temperature? of the gases? Does it change it to something else?
Ooh,
What does gas become when you are lowering down the temperature?
liquid.
Liquid, and then
And then solid.
those are some of the logical processes that's there, right? And when we measure temperature, what are we really measuring? We're measuring the behavior of these gases using thermometer. What are we measuring when we're measuring the temperature? We mentioned this last time. What is a,
Heat.
what do we measure? What do we measure, Michelle? You can take a look at the screen here. What are we measuring when we're measuring, taking the temperature?
We're measuring the movement of the gas and also the pressure. Yeah.
Yeah, we're measuring the average kinetic energy, right, how they're moving. So everything, you have the simulator in front of you. You can just look at this, and that's summarize of all of the behaviors that gases take on. There's a lot more, but I just take some of the basic principles. You ready for liquid conversation?
Yeah.
Ready to talk about water? Why is water so special? And when we talk about life, we have to live on water. Why is it so special?
I think there's two main reasons. So first of all, water can dissolve lots of things.
Beautiful.
It's a universal solvent. And second of all, I think this is what you want me to say. The ice is less dense than the water.
Good. There's a lot of extraordinary properties of water that supports life, right? We're going to take a look at how those things come together into real life pictures. So what is the general shape of water? We give it a nickname. What is the nickname called? Let's take a look at the pictures here.
A random blob.
Random blob. They're called the Mickey Mouse. They're Mickey Mouse molecules. Don't they look like a Mickey Mouse?
They look like a random blob to me.
Try to trace it. Not a heart, but it's a Mickey Mouse, right? So they're made of H2O, right? There's H2O. Because of their structure, the way it's arranged, this triangle style, that makes it very special. Moving on. Okay, so are there charges in water molecules? Meaning, are there positive and negative charges, or are they just neutral? So water molecules is polar, and that is also crucial for when we talk about, right? So when you mix water and oil, do they mix? They don't mix. Have you ever mixed water and oil together? If you try to cook, it's gonna splash, right, with water and oil together. And the reason is water is polar, oil is non-polar. Polar means it has a positive and negative end to it. But the overall nature of water is zero. So you touch water, you're not gonna get electrocuted, right? Because the charges are balanced. But when you're looking at the individual end of the molecule, there's some positive and negative charges at the end, just because how the electrons are pulling against each other. And I'll go into more details about these names about electronegativity, but for now, just to understand that some elements attracts electrons greater, with more energy. So this charge, this polar charge, allows different molecules of water form a bond. This bond is called hydrogen bond. It's a very strong bond within, molecularly, between particles. That allows, remember we said water has a high boiling point? In order for water molecules to be free from each other and to change into gases, they need to break this bond. And that bond requires a lot of energy. So because a result of interactions like this, because of the hydrogen interaction, we're going to see a lot of special properties. Water takes Boils. What's the boiling point of the water? At what temperature does water boil?
I think it's 212.
So depending on the sea level, right? So we are pretty close to sea level. So it's 100 degrees if you're exactly at sea level. If you're increasing at a higher level elevation, then there's gonna be less. You're gonna require less temperature, lower atmospheric pressure because there's less gas particles above us. So if you're on a mountain, the water boils a lot quicker. But that also means the temperature is not high enough and you didn't kill all the bacteria. So be very careful if you ever climb the Himalayas and you try to boil water up there. Be very careful. And here's a good simulation, right? That's why if you go up on the mountains and you try to boil egg in water, it's going to take longer to boil because the temperature doesn't get very high. Temperature does not get very high. Okay, remember we talked about hydrogen bonding, that molecules are attracting, water molecules are attached to each other with a very strong force. As a result of that, here are some of the qualities that water brings to life. Harry mentioned high specific heat. We're going to talk about all of that. Less dense and less dense. And so cohesion. Water is attracted to itself. Has anybody seen one of these bugs walking on water? Jason?
Yeah, isn't that like surface tension?
Surface tension. So there are actually two forces. Absolutely. Surface tension. Nice bringing that up. But how does surface tension form? Because of the attraction of water molecules. They have a strong force, right? It's like magical. If you're light enough, you're able to walk on water. Why is this important for the survival of a species?
Because you can get to other animals by walking on the water.
Absolutely, right? You can run away from your predators or seek more food. Adhesion. This is the attraction between different substances. So water not only going to attach to itself, it also attracts to water, glass, soil, plant tissues, cotton. Every time I wash my hand, I try to dry my hand. The water doesn't want to get away. It's always sticking on my hand. Let's take a look at how that's helpful. What happened if I take a straw and I dip it in a bowl of water? What happened to that water? What happened to the water if I dip it in a bowl of water? Michelle, what do you think? Have you tried this in elementary school? You try it. Well, Kevin, have you tried it?
Oh, well, I've done that many times. Wait, do you mean like you put the straw in the water and you cover
Oh yeah,
the
and then
bowl?
you use your
Yeah.
hand and suck it.
I
Yeah,
do that. Yeah.
yeah, we do that a bunch of times.
Yeah? So what are you trying to show?
I don't know. It's fun.
It's the ability to travel against gravity, travel upward. Now, you ever go to the doctor office? They're trying to get blood from you. They use, well, there's like something called a capillary tube. We can just dip it on your water. If you just like get a piece of, a little bit of your blood, and they can extract that blood upward through that tube. Why does that happen? Right, so there are many applications. I've done some research on this.
Oh yeah, this thing.
Tell me more about this experiment. What do you get from this experiment?
I think we did this like when we were little in school. Yeah. Is that like color dye?
Yes, we have color dye in the water.
Celery?
We have celery and leave it for a few days. And what do you see?
Well, the blue grows the tallest.
Well, they are originally different sizes, right? But these dyes travel, these colors traveled upward, right? Isn't that against nature to go away from gravity? To travel away from gravity?
No, but like plant roots can suck water.
How does
They're uprooted. Aren't they uprooted though?
So this is called a capillary action. Plants have the ability to bring water up, right? This is through by using what's called the capillary action. Capillary action is the ability for water to travel upward, provided that the tube had to be very skinny so the water attaches to the side. The skinnier the tube, the faster it travels upward. I'm going to show you a simulation of how this works, not a simulation, a demonstration. Water are attracted to each other, right? So that's called a hydrogen bond. Water has the ability to attract to the walls, right? See, these are the walls. They attach to them and push them up, like kind of squeezing them upward. So there are two forces. There's the force at adhesion. They're holding hands with each other. And cohesion, they're holding hand with each other. Adhesion is they're holding hand with other materials. All of these forces push along for them to travel up. What is this process called? It's called capillary action. All right, so you've done the experiment. You try with the towels. You make a rainbow. You can do it with any type of plant. Doesn't have to be a celery. Does anybody use fountain pen? This is very popular in Asia. Does anybody use this fountain pen?
What?
I have one, but I don't use it, and I don't use it. It's like I don't have ink bottles. I just like you put the ink into the pen,
and the liquid will move upward, right? That is capillary action. Talking about some applications of water capillary action, right? Your blood vessels, the blood travels through capillary using a capillary action. When you have tears, the tears are created in the tear duct, in the tear gland, and it travels upward through capillary action. In soil, right? Water, underground water, seeps through these soil gaps through capillary action. This allows for the filtration for the collection of water reservoir. Lots of these, right? So adhesion also causes things like these, right? You see these little droplets along the plants. It allows the water to attach the spider webs. Okay, Harry, I'm going to take this to you. You talked about high specific heat. Can you read that again or tell us what is high specific heat? Water has
a high specific heat. So specific heat is how much energy you need to raise the temperature of a substance of 1 gram of a substance by 1 Celsius.
Yeah.
So water, I think you need like 4.1 something joules.
Yeah, 4.18 joules.
For other substances, you need less energy, like maybe 1 joule.
Yeah. And this is application of this. What does it mean, right? Water takes a long time to heat up.
But it also takes a long time to cool down.
So does anybody go to the beach and swim?
Mm-hmm.
You do?
So even though the water is shining in the sun all day,
yeah,
it's still pretty cold.
So in the summertime, because it went through the whole winter, right? It's still absorbing the summer heat. So the summertime, early summer, the water is still very cold. But at the end of the summer, the water will become like a little warmer. Also, another way to think about it is weather. When you're in a desert area, it gets extremely hot and cold because it does not have enough water vapor in the atmosphere. The water has the ability to hold on to that heat. When you don't have cloud covers, that heat is not retained. It goes away right away when the sun sets. So that's what we say, that water supports life by holding on to that extra energy to give us that time to compensate for the change of time. Hydrogen bond has a high heat of vaporization. That just means, another way of saying, has a high boiling point, right? You had to break down the bond. What is a bond called between two water molecules? What's that called? What's the bond in between attaching the water molecules? What is that called? It's called a... Ben, haven't heard from you. What is the bond that is attaching the molecules of water? Start with an H.
Hydrogen bonds?
Hydrogen bonds. Good. And because of that, we have high heat of vaporization, high boiling point, high specific heat content. Now, if you're interested in more, you can go dive in, right? So this actually explains what we're trying to explain here. Water, the Earth has a warm surface because the water vapor is retaining that heat, right? Imagine the minute that the sun goes down, there's no water vapor in the atmosphere, it becomes super cold. So environmentally, it's cool. Water is less dense than solid, right? So let's take a look. Which one is a solid? Which one is a ice? Which one is water? Michelle, which one is ice? And then if I just say 1, 2, let me just label 1.
I think one is ice and 2 is water.
Okay. Anyone else have a different idea? What about you, Brian? What do you think? Which one is ice? Which one is water? It's okay. We're just taking a guess.
I think 1 is ice and 2 is water, since 1 is more compact together.
Isn't 2 ice because 2 is a crystalline structure?
Yes, and that is the beauty of this hydrogen bonding. When water freezes, it creates this lateral structure, which makes it less dense. So ice structure has these, you can think about snowflakes. They're kind of spread out. That has the lateral structure, makes it less dense. So, but going back, that's a special property of water. All right, so water has the ability to maintain a steady state, right? It's a good insulator and you can keep the temperature the same for a long time. It's a universal solvent, like Harry said. It dissolves almost everything in the world, right? I cannot imagine without water. Like I am obsessively washing my hands all day.
Can I say something?
Go ahead.
So if ice was actually more dense than water, then when everything froze in the winter, then the ice would float to the would sink to the bottom.
Yeah.
And then in the summer it would still be in the bottom and it wouldn't melt because it's at the bottom.
Yeah.
And then it would eventually accumulate until like the water was really shallow.
Also, think about all of those habitats up in the Arctic that supports living things, right? Those are not going to be possible. The ability for ice to flow on top of water allows the animals to travel. So in terms of solution, water dissolves everything, right? If I get my hand dirty, I soak my hand in water, it comes right off, or it takes some days to come off. Things that's hard to come off, I put some soap, right? That helps the surfactant help it to bring it off. So there are 2 types of mixing when you mix it in water. There's a group that actually dissolves in water, and there's a group that suspends in water. A solution is when, like, you put sugar in water, those sugar molecules will break down and mix it in water. That's a solution, you're mixing it. A suspension, like that's things that don't dissolve in water but still be there, like any type of like a mayonnaise. Those are made in mixture of water. Those they don't dissolve completely. They just become suspended. Same thing with milk, right? It's a permanent suspension there. Until the milk goes bad, you see the separation of the materials. So acid and bases, right? Water, another way to think about water, it has a neutral pH. When it breaks it apart, it breaks into more acidic or more base. A little bit introduction about what that means is when you have, this is just a scale of an acid or water acid, right? Things are like orange juice, tomato juice, vinegar. Anything from 0 to 6.9 is considered acidic, right? Tastes sour. And in the middle is pure water. Pure water is neutral, which allows life, right? It brings the balance for life. Can you imagine without water, these things are not neutral. Anything above 7 to 14, like this is just a scale of measurement. Like human blood is a little basic. Like these are bases like bleach, ammonia, soap, seawater. And then you have these buffers that kind of neutralize the environment around us. There's a little weak acidic or weak space. So to conclude, I just want to take one thing from you, one thing that you find that surprises you or important or fun that you learned that you like to share with us. I want to, before you head out, just type in one thing you learned today. I know there's a lot of information, but if you can keep one interesting idea, go ahead. Ben?
The acidity chart. The chart.
You want to see it again?
Yeah, that chart. I found it was interesting.
Okay, so type it up. Good. Type it up. If you want to say it, thank you. If you've said it verbally, you don't have to type it. If you want to just type it up, we'll share with the class all the interesting things you've learned. Anyone else have anything to share verbally? Harry, you have anything?
Not really.
Is that a picture of you in the back?
Yeah, when I was not very old.
Like what, 2 years old or 3?
When I was like 1.
Wow. Nice. Michelle, do you have anything to share, like what you learned today? Any thoughts? Any thoughts, Michelle?
I don't really know.
I don't know. What do you remember that we learned?
Yeah, I remember a lot, but then when it comes to writing about something that you found interesting, it's kind of hard.
Okay. Kevin, what about you?
I don't really know.
Is that a lot of information for you guys?
Something I found interesting.
It doesn't have to be interesting or surprising or just simply something you learned. What is one thing you learned today?
How thermometer works and the mercury.
Okay, good. What is one thing you learned, Jason?
Water is capillary.
Capillary action, has a capillary action. Good. What is one thing you learned, Brian?
I like the simulations.
Good. Isabella, you can write down your thoughts down there. Hydrogen bond. Oh, Isabella said she uses a quill. A quill is, oh, nice. Not a fountain pen, but a quill. That's good too. It definitely uses capillary action, takes in the ink. All right, so I wish you a good weekend. Really enjoy. Hopefully we don't get a lot of rain.
Bye.
Hi.
Bye.
Thank you.
For you guys. Bye-bye.
Bye.